In this lecture, let us complete our discussion on supersonic wind tunnels, and then we will discuss a little bit about dimensional analysis. So, in the previous lecture, we had discussed about continuous closed return supersonic wind tunnel, if you recall. We are looking at the diagram once again, and in today's lecture, we will try to estimate the power requirement for running such a tunnel. We will consider that the wind tunnel is running in steady state. So, in such a situation, the energy content of the system will remain time invariant, and the work performed by the compressor will exactly be equal to the heat removed by the cooler. So, this is the condition under which we are trying to do the estimation, and we will also consider the different processes involved as ideal. So, in the compressor cooler combination, what we are trying to achieve is essentially removal of the entropy increase due to dissipative processes in the flow. So, there are losses involved, and that loss has to be offset by the compressor cooler system. The entropy removal per unit mass can be given by this relation R log P naught by P naught dash, which is nothing but R log lambda, where lambda is the wind tunnel pressure ratio, which is the ratio P naught by P naught dash. And then when you consider the mass flow rate, then you will be able to get m dot times delta S, which is the total entropy removal that has to be taken care of. Assuming that the heat transfer at the cooler occurs reversibly at constant pressure, we can write down the expression per unit mass for the rate at which the heat has to be removed. That is given by Cp times Tc minus T naught, which is incidentally also equal to small w, again per unit mass. The temperature is identical across the cooler and compressor. If you look at the previous diagram, you will be able to see that. And if you assume that the compression is happening reversibly, there is no entropy increase there, then the temperature ratio can be connected with the pressure ratio using the isentropic relation, which we have stated here. Thereby, you are able to express the Tc by T naught in this equation in terms of P naught by P naught dash, which is lambda, through this expression. Ideal wind tunnel power requirement will therefore be m dot into W, which is given by this expression. We would further write down an expression for m dot, considering that the throat is choked based on the star conditions at the throat, which gives you this equation. And finally, we come up with an expression for ideal power, where we further use the perfect gas equation of state to bring in P naught. So, this is the final equation where we consider that all the processes involved are taking place ideally. So, this is essentially the minimum power required to run it under ideal conditions. In a real tunnel, the power requirements will obviously be greater than this. What is the ideal power dependent on? That is very important for us to understand. It is dependent on stagnation pressure P naught, stagnation speed of sound A naught, throat area, that is A star, and the a function of overall pressure ratio, because lambda here does not exist as a independent term, it has an index gamma minus 1 by gamma. So, this approach gives you a method by which you can estimate what would be the power requirement for your closed circuit continuous supersonic wind tunnel. So, with this we are ending our discussion on the closed circuit supersonic wind tunnel. The next topic that we are going to get into is a very important tool in engineering in general and in experimental aerodynamics in specific, which is called as dimensional analysis. And there is a very, very important theorem which we will briefly describe over here, which is called as the Buckingham pi theorem, which helps us to implement the dimensional analysis. We begin by saying that which physical quantities determine the variation of forces and moments on an aerodynamic body like an aircraft or an airfoil or an aircraft component, etc., can be answered better if you make use of this very useful engineering tool called as dimensional analysis. So, here in the two diagrams which are very familiar to us, we have shown the different forces and moments which act on a complete aircraft or a component like an airfoil section, and we are trying to understand that which physical quantities determine these forces and moments. Now, based on our existing knowledge of aerodynamics, we can say that if we are looking at the airfoil problem, the resultant force which acts on the airfoil, when it is fixed at a certain angle of attack, it is dependent on density, velocity, that of the free stream, then its size, which could be the chord length of the airfoil, the viscosity of the medium, again referring to the free stream values, and additionally if the flow is compressible, you have to bring in the compressibility effect of air into account by introducing the speed of sound. Therefore, the resultant force R can be functionally represented in terms of rho infinity, u infinity, c, mu infinity and a infinity. So, here are these independent variables which would decide what would be the value of R for a particular angle of attack. Remember that we are fixing the angle of attack. Now, if you want to address this problem and try to find out what exactly is the functional relation here, one way could be that you mount the airfoil model in the wind tunnel at a certain angle of attack and then you measure the variation of this force R. How? By varying all the independent variables one at a time. So, what will happen? You will get a lot of plots which will be generated through the acquired data, and then hopefully you will be able to obtain the desired equation which connects the independent and dependent variables. However, this will involve a lot of effort, a lot of time and a huge amount of wind tunnel experiments which involves both cost and time. However, if we use this very important tool called as dimensional analysis, you can simplify this process considerably. So, we are going to understand how we go about doing that shortly. We make use of this Buckingham pi theorem, and what we are going to see in the next few steps is basically the principles embodied within this theorem. We will define k number of fundamental dimensions which are required to describe the physical variables. When we consider that this airfoil is being tested at low speeds, the physical variables can be expressed in terms of dimensions of mass, length and time alone. When it is going to be a compressible flow, additionally you will have to bring in temperature, because we have already discussed that thermodynamics aspects of the flow become important. So, at low speeds we consider that mass, length and time would be sufficient to explain all the physical variables, and therefore, the number of fundamental dimensions is 3. Additionally, we will account for n physical variables which are sufficient to describe the physical relation given by this function, which is not known to us yet, but we are representing it in this form, where the n number of physical variables are the independent variables. Then the physical relation given may be re-expressed as a relation of n minus k dimensionless products. So, from dimensional physical variables which are n in number, we are now going to a lesser number of dimensionless products which we will call as pi products. Of course, these dimensional physical variables which are n in number will be combined in some sense to give rise to these n minus k number of dimensionless products. So, this is the representation of the pi products. And how do we define each one of those products? The rules are given here. Each product is a dimensionless product of a set of k physical variables. So, in our case, for the low speed flows, k is equal to 3. So, 3 physical variables plus one other physical variable. That means, each pi product will therefore have 4 physical variables involved. Now, these 3 physical variables that we choose will be fixed for each pi product. Only the one additional physical variable will be changing from one pi product to the other. So, that is how we define the pi products here. You see, in general they are shown like this: P 1 to P k followed by P k plus 1 for the pi 1, and P 1 to P k for pi n minus k, which is the last pi product, followed by P n. In our case, k is equal to 3. Therefore, we have P 1, P 2, P 3 which are fixed, and the last one varying from P 4 to P n. That is how we would generate our pi products. Let us go to the next step. Choice of the repeating variables should be such that they include all the k dimensions. So, they must include all the k dimensions, which are 3 in number for us used in the problem, and the dependent variable, which is r in this case, should appear in only one of the pi products. So, these are the additional rules which we have to keep in mind. So, this is the r equation that we are familiar with. You can also write it in a form like this, where r joins the list of variables and you have a function g equal to 0 representing the situation. In this form, g equal to 0 form, you can count the n's, that is the number of physical variables. You already have a count of 3, a count of k, which is 3 for you. Thereby, you now have the number of pi products, which is given by n minus k according to the Buckingham pi theorem, which turns out to be 3. So, you can expect 3 pi products for this problem. Now, coming to identifying the dimensions of each of the physical variables, which also includes r now. So, these are the 6 of them. Now, r is a force, and you can use the Newton's second law, force equal to mass into acceleration, to derive its dimensions. You can check on your own later. Density, velocity, chord length, viscosity, and speed of sound. For viscosity, again you can use this relation, shear stress equal to mu times the velocity gradient, which can help you conveniently to define its dimensions. So, you must do these things on your own later at home. We are identifying the blue colored variables as the repeating variables P 1, P 2, P 3. Why? Because if you combine them, you have M, L, T, all the k dimensions included. Now, coming to defining the pi's. So, there are 3 of them, pi 1, pi 2, pi 3. You see, these are the repeating variables, and the last one is the one which is non-repeating. Only one of the pi products contains r. So, we have followed all the rules while forming the pi products. How would we express pi 1 to begin with? Let us do it this way. You form a product of all the variables, but you raise P 1, P 2, P 3, these 3 variables which are repeating, to 3 different indices, which at this point are not known to us what the values of these indices are, but we have to find them out in some way. So, that we end up forming a non-dimensional group here. That is the crux of the thing. So, these indices at this point are unknown. Now, if you represent phi 1 dimensionally, then what have you got to do? You have to represent rho infinity in terms of its dimensions. This should be in the index. Then u infinity, c all in dimensions and raised to the respective indices. And finally, you have the dimensions of R. Since pi 1 is dimensionless, net index of m, l, t individually should be 0. What does that give you? For each one of them, you get an equation, so that the net index is 0. So, they form 3 simultaneous linear algebraic equations, which can be solved easily to get the values of p, q and s. Once you have them, let us see what pi 1 is. Pi 1 has come out to be r by rho infinity u infinity square c square, which can be rewritten like this without affecting the dimensionality, because you still have a non-dimensional group here. Only thing is you have associated a half here, so that you can identify it as a free stream dynamic pressure, and instead of c square, c being a length scale, c square will represent some area. So, you are assigning a certain reference area, which may be the chord of the airfoil into unit span. That may define your area. So, this basically gives you a non-dimensional force coefficient. In a similar manner, if you solve the problem for pi 2 and pi 3, this is what you are going to end up getting, which you should again try doing independently. What does this define? It defines Reynolds number based on the chord of the airfoil. What does this define? It defines Mach number. Revisiting the pi function, we now substitute the values of pi 1, pi 2, pi 3, because we have all worked out these values, and therefore, we can now write the pi function like this. So, the non-dimensional groups here are CR, RE and M infinity. You can rewrite this functional form like this, that CR is equal to FR RE M infinity. So, CR is a function of Reynolds number and free stream Mach number. So, CR is a resultant force. If you resolve it into components, you are going to get CL and CD, provided you substitute the angle of attack. And remember that this functional relation has been worked out for a fixed angle of attack. If you had varied the angle of attack, then CR would obviously come out as a function of Reynolds number, Mach number, alpha as well. So, that is how you get CL, CD as functions of Reynolds number, Mach number, angle of attack. If you work out a similar relation for pitching moment, you will get it functionally like this. A large portion of theoretical and experimental aerodynamics is focused on obtaining explicit expressions for the above equations for specific body shapes. So, if you vary the body shapes, these expressions would change. So, for one body shape, it will have a certain functional form. If you change the body shape, it will be something else. What have we achieved? We started from here, and R at that point was expressed as a general function of 5 independent variables. When we applied the steps of Buckingham pi theorem for the dimensional analysis, we expressed a non-dimensional force coefficient CR, that was through the pi 1. Further, we could express that CR is a function of Reynolds number and Mach number. So, we have reduced the number of independent variables from 5 to 2 basically. Now, if we wish to run a series of internal tests for a given body like the airfoil at a given angle of attack, we need only to vary the Reynolds number and Mach number in order to obtain the data for the direct formulation of R through this equation. So, we have simplified the problem dramatically by making use of this theorem. So, with a small amount of analysis that we did, we have saved a huge amount of effort and internal time. More importantly, we have defined two dimensionless parameters, Reynolds number and Mach number, which were known to us from other means, but here we obtained it through a very practical engineering approach. We thereby learnt the dimensional analysis approach of deriving such dimensionless parameters, and they are very important parameters which govern the flow. They are called as similarity parameters. The significance of the term will be discussed further in an upcoming lecture again. There are different kinds of similarity as well, which we will discuss. So, this was about how we do it in low speed aerodynamics. What will be the augmentations, the additions when we look at compressible flows? Let us try to have a brief look on that. So, for compressible flows, we know that when the free stream Mach numbers become high supersonic or hypersonic cases, then thermodynamics due to very high flow velocities and heat transfer due to the viscous effects in the boundary layer become very, very important. So, as a consequence, free stream temperature, that is T infinity, specific heat Cp, Cv, thermal conductivity of the gas, temperature of the body surface, that is the wall temperature, these become additional physical variables. So, they add on to the list of n. Temperature with its accompanying dimension Kelvin in SI units must be added to the list of fundamental dimensions. So, it adds on to your list of k. In the low speed case, we took k equal to 3, here it will be k equal to 4. Dimensional analysis yields additional dimensionless products. So, you will have more pi products to look at, like heat transfer coefficients, say Nusselt number. Dimensional analysis yields additional similarity parameters, such as ratio of specific heat at constant pressure to that at constant volume. So, the gamma, the ratio of wall temperature to free stream temperature, T wall to T infinity ratio, and Prandtl number, mu infinity Cp by k infinity, where k infinity is the thermal conductivity of the free stream. So, these are the additional considerations or additional aspects that one has to keep in mind for performing a dimensional analysis of compressible flows. To conclude, in this lecture we learnt about how to estimate the ideal power to run a continuous closed circuit supersonic wind tunnel. Subsequently, we discussed about dimensional analysis using the Buckingham pi theorem, which helps us identify similarity parameters for use in aerodynamics experiments both at low speeds as well as high speeds. Thank you.